Today we're going to be talking about normal force and the force of gravity. And every now and then I'm going to ask you to pause and try and answer one of the questions so that you get the experience that you would have had in the class. So right now I'm going to go ahead and ask you to read question 1, give it an answer, try and answer question 1, and then go ahead and watch the video that we have linked right here. After you've done that, come on back and we will talk about the answers to those questions. All right, great. Hopefully you went ahead and you answered that first question and you realized that it was the force of gravity that keeps the moon in orbit around the Earth. And then hopefully you saw the video with the astronauts in space and they certainly appeared weightless. And it often is the case that people will answer that the reason those astronauts appear weightless is that there's no gravity in space. But we know this can't be true because you just told me that the force of gravity is what keeps the moon in orbit around the Earth. So we know there's gravity there. So we have to come up with another answer. And you might not see another answer yet, but we're going to get there. So what I want you to do now is go ahead and read through the next couple of questions and go ahead and answer question 3 for me. Go ahead and pause and read all that and then answer question 3. All right, if you answered question 3, you might have put that you think that a scale measures weight. Maybe you even put mass. That's not correct. We've got to figure out what the correct answer is. So based on this equation right here, what are the only two variables that affect weight? We're going to write their symbols here. Hopefully you see that mass affects weight and that the acceleration due to gravity affects weight. Those are the only two things that will affect weight. So let's go ahead and let's go to that next page. So knowing that mass and the acceleration due to gravity are the only things that affect weight, you should see that there's nothing you can do while you stand on the scale to affect your weight, because you can't affect your mass. You can't change your mass. We're not going to eat anything or put additional clothes on. And there's certainly nothing you can do to change G. You can't leave Earth while you're standing on the scale. So as you stand on the scale, there's absolutely nothing you can do to change your weight. So hopefully you see that a scale does not measure weight. But let's think about a couple things. I think that if you stand on the scale, you can think of some things you can do to increase what the reading is on the scale. So try and think of something you can do to increase and decrease your reading on the scale as you stand there. Go ahead and pause the video and put something in there. All right, to increase the reading, there's a couple different things you could do. You could have, if you're tall enough, you could have put your hands on the ceiling and pressed down on the ceiling, or I guess press up. If you're not tall enough for that, you could have instead grabbed maybe a counter. And if you try and lift the counter up, the counter will actually push you down. So if you lift counter up, that would have also changed and increased the reading on the scale. To decrease the reading on the scale, a lot of people say, oh, you can lift one leg. Actually, that won't change the reading on the scale. What will change that is if you press down on a counter. Almost like you're lifting yourself up on the counter. If you do that, you're going to decrease the reading on your scale. Now, we know that that doesn't decrease your weight or change your weight, so something else is happening here. The scale must be measuring something that's not your weight. And it does measure another force. So let's think about what other forces it can be measuring. So let's go ahead and draw a free body diagram of you as you stand on the scale. I'll get you started. Go ahead and draw that little dot, and then tell me what forces are acting. Hopefully you know that force of gravity is one of those forces, and it's always acting down. And the normal force exerted by the scale on you, because you're standing on the scale, is the other force. So the only force that's acting on you besides the force of gravity is the normal force. Then the question becomes, is it possible to change the normal force acting on an object without changing the object's weight? It absolutely is, and let's see how. So consider a book sitting at rest on a table. So here's the book, and just like you on the scale, there's a force of gravity down, and there's a normal force up. And as it sits at rest, we know those two forces have to be the same. But now let's think about what happens if you have the book at rest and you push down on the book. So now we've got not just the force of gravity going down, but we also have an applied force going down. We still have that normal force going up, but that normal force has to get bigger because it has to account for both the force of gravity and the applied force. And if it wasn't the same size as both of those forces added up, then we know the book would be accelerating through the table. Well, it's the job of the table to make sure the book doesn't accelerate through the table. So this force here, this up force right here, has to be the same length of these two forces down. So clearly there is a way to increase the normal force without changing the force of gravity. So if we think back to that original question, and I'm looking at question 10 now, when you increase the reading on the scale without changing your weight, what force do you really change? Well, you're really changing the normal force. You're not changing your weight, you're really changing the normal force. So when you decrease the reading on the scale, what force do you really change? You're changing the normal force. What force does the scale read? It does not read the force of gravity. It reads the normal force. So whatever the normal force is that's acting on the scale, that's what the scale is going to show. So let's do a little bit of practice now. Okay, and if I'm going too fast, absolutely pause the video and read all the words that I'm kind of skipping through. Okay, so question number 13 asks, all right, what's your mass if you stand on a bathroom scale and the scale reads 800 newtons? Well, we're not always used to seeing the question phrased that way, but this is what we're asking. We're saying, well, we know the force of gravity. Because if you stand at rest on the scale, we know the normal force does have to equal the force of gravity. That's why a scale is often used to measure your weight. So if the normal force is 800 newtons and you're standing at rest, then your force of gravity on you, or your weight, is also 800 newtons. So we can say that 800 newtons is equal to m, which we don't know, times 9.8 meters per second squared. Well, then I can solve for m. So when we do that calculation, we find that m is going to be equal to 81.6 kilograms. Okay, that's just a little bit of practice. Another misconception we want to address right away is this idea that when you are in the elevator, you experience a force of tension. So the tension force usually comes from the cables that the elevator hangs from, and people like to think that, oh, well, there must be a tension force involved on you. But there's not a tension force on you because you are never touching those cables, right? That's a no-no when you're in the elevator. You shouldn't be sticking your hand out trying to touch the cables. So when in an elevator, I do not feel the force of tension from the cables because the cables never touch you. So make sure you understand that as well. Okay, so let's get to our elevator ride. Now, we're going to try a couple different thought experiments. And for this first one, we're going to think, all right, you're on the elevator, and there's a scale, and you're standing on the scale. And the elevator is moving up at a constant speed. We want to know what amount does your scale read. So to get that, let's go ahead and start by drawing a free body diagram. And I think everybody knows now we're going to have a force of gravity down. We're going to have a normal force up, no tension force. And we have to figure out, well, is that normal force bigger, smaller, or the same size as the force of gravity? I would like to argue, and you can think about this if you want to pause the video, I would like to argue that it's going to be the same size as the force of gravity. It has to be, because if we're going at a constant speed, that means the acceleration on us is zero. Well, if the acceleration on us is zero, then the total force that's acting on us also has to be zero. Well, if the total force is zero, that means the down force has to be perfectly balanced by the up force. They have to be equal, which means then that the normal force has to equal the force of gravity. We know the force of gravity is 800 newtons. So that means the normal force will also be 800 newtons. And since the scale reads the normal force, the scale will say 800 newtons. Similarly, if we're on the elevator and the elevator is moving down at a constant speed, we're going to see the same thing. We're going to have a free body diagram that says there's a force of gravity down, there's a normal force up. They have to be equal because, again, our acceleration is zero, our total force is zero, so our bathroom scale is going to read 800 newtons. If we change up the situation a little bit and we look at 17, in 17 we're going to again be riding the elevator, and it's going to be going up, but it's also accelerating up. Okay, so this happens if you're on the ground floor, you press the button, the elevator starts to move. It must be getting faster on the way up, at least for part of the trip. So that means we have an acceleration up. This free body diagram is going to look a little different. So let's start by understanding the F total. If we are accelerating up, so if our acceleration is up, the F total also has to be up. That means, okay, and it's not that the acceleration is equal up, it's just the acceleration is up. That means that the up force has to be bigger than the down force. So let's see what our free body diagram looks like. We have a force of gravity down. We're going to have a normal force up. A lot of people misinterpret this as saying, oh, there must be an applied force up as well. I mean, after all, I'm accelerating up, there must be an applied force. And the question I ask when people make that assumption is, well, what's applying this force? It's not the tension from the cables. We already talked about that. It can't be. Well, what else are you touching? The only thing you're touching is the scale. So the force of gravity is acting on you, but the only thing that's touching you is the scale. The scale is applying the force on you that is making you accelerate up, and that's the normal force. So in this case, the normal force has to be bigger than the force of gravity so that you will indeed have an acceleration up. That means since the normal force got bigger than your force of gravity, the scale is going to read more than your weight. Now let's look at a similar situation, but now your direction is in the down acceleration, is in the down direction. This happens if you're on the ground floor, you press the 5th floor button, but once you get to the top, right, you're approaching the 5th floor, you start going slower. So your velocity is up, but you're getting slower. So remember from our kinematics discussion and our acceleration discussion that if you're going in, if your velocity is one direction and you're getting slower, the acceleration must be in the opposite direction. So if our velocity is up, but we're getting slower, then our acceleration has to be down. Well, if our acceleration is down, then our total force also has to be down. What's that free body diagram going to look like? Well, our force of gravity couldn't change because our mass didn't change and G didn't change, but our normal force has to be less than the force of gravity. So our normal force is decreased, so it will no longer equal our weight or be more than our weight. Now the normal force will be less than our weight. So now we can see why the scale changes its readings. So now let's do another little kind of thought experiment. Okay, so imagine now you're on the 5th floor and you want to go down. What direction are you moving in? Or a better way to put this is, what direction is your velocity? Well, we know your velocity is down. So let's think about our accelerations and our total force in this situation. So at the beginning of the trip, the elevator's not moving. Then it starts moving down and it's getting faster on the way down. So our velocity is down. We're getting faster. That means our acceleration has to be down. So for the first part of the trip, you've got a downwards acceleration. So your total force has to be in the down direction. After a little bit of time, the elevator will have reached its cruising speed. Now you're going at a constant velocity. If your velocity is constant, so I'm looking at question 21 now, if your velocity is constant, that means your acceleration is 0. As you get closer to the end of the trip, for question number 22, you have to get slower, right? You can't jump out of a moving elevator. So as your velocity continues down, you're getting slower. That means your acceleration has to be up. So think about which forces will be greater in each of these cases. If we look back at question 20 and your acceleration is down, that means your total force must be down. That means that the normal force must be less than the force of gravity. For the middle part of the trip, when we're going at a constant velocity, that means that the normal force has to equal the force of gravity. And when the acceleration is up, that means the normal force has to be greater than the force of gravity. Now let's think of another little thought experiment. You're standing on the elevator, and the unthinkable happens. The elevator cables snap. You are plummeting to the basement. The elevator is falling, you're falling, the scale is falling, everything is falling. What does this free body diagram look like? Go ahead and draw that now. Pause and draw that now. Well, hopefully you drew a free body diagram with only the force of gravity acting on you. If that's the case, and the force of gravity is the only thing that's acting on you, that means your acceleration is 9.8 meters per second squared. And if the only force acting on you is the force of gravity, and there's no normal force between you and the scale, that means the scale now reads 0. This is weightless. Only you're not weightless. It feels different, absolutely, but the name is incorrect. So go ahead now and pause for a minute and go ahead and read the rest of this page. Okay, now let's talk about our astronauts again. But first, let's look at a little thing, because really what I'm getting at is that you are weightless when you are in the falling elevator. Again, it's not named great. You're really normal forceless. So does that mean that the astronauts are also falling? And people like to say no, but let's see if that's wrong. So let's take a look at this is the Earth in green, and this is just a thought experiment. We have a really large, tall mountain, and at the top of the tall mountain we have a cannon. And from the cannon we shoot a cannonball, and the cannonball goes out and lands at point A. Then we go ahead and we get a stronger cannon, and we shoot the cannonball out even faster. Well, now the cannonball doesn't land at point A, it goes all the way at point B. And if we could shoot it even faster, it might land all the way over here. We didn't name it, but maybe at point C. But if we had a really strong cannon, we could shoot the cannon so far, so fast, that the ball would fall at the same rate of curvature as the Earth. So the ball would be falling and would never hit the ground. That's what's happening with the astronauts. They have such a large velocity that they are constantly falling, but they never hit the ground. It is exactly the same as you on the broken elevator. You're falling, and so is the astronaut. The only difference is the end. The elevator will hit the ground, rough end. The astronauts will never hit the ground. They will fall forever. That's all that an orbit is. An orbit is simply an object that is falling and never hits the ground. Thinking about that, now I think you can go back and answer the first question or the second question that we asked about what makes the astronauts appear weightless. They are in a constant state of free fall. This last part asks about a friend of yours. So go ahead, pause the video here, and read the rest of this page down to the question we asked in 26. Okay, so your friend is contending that the reason that the space station keeps going around is because of the less G. And I agree to a point. There is certainly less acceleration due to gravity at the altitude that the space station orbits at. But certainly that's more than enough to keep having a weight or a force of gravity on the space station and the astronauts. So that's not it. This right here tells me that there's more than enough gravity, more than enough acceleration due to gravity and force due to gravity. Even all the way to the moon, we still have an acceleration due to gravity. So this data certainly does not help explain or support my friend's statement. Okay? All right. That's all I've got for you today. Hopefully you understand normal force and the force of gravity a little bit better. If you don't, great time to ask questions next time I see you in class. Bye-bye.